So in the last few classes, we looked at sorting algorithms. We looked at varieties of theta n squared or order n squared algorithms. As I said, we do not distinguish between theta n squared and order n squared. We take the tightest bound. There are other varieties of sorting algorithms which do the problem in theta n log n. And we look at these algorithms during the next week. Now, I want to do a few algorithms called searching algorithms. And what is a searching algorithm? Remember, all these algorithms are with respect to the ADT array. We want to search for a given element in the array, in an array. Okay. So there are different types of searching algorithms. We have linear search, binary search, ternary search. There's also something called indexed search and so on, but the scope of the course is only up to this. So let us look at linear search algorithms. In this we have two varieties: searching in an unsorted array and searching in a sorted array. Binary search is always in a sorted array. Okay. So first let's look at linear search in an unsorted array. So let me write this as a function module, which will return the index of the location of the element if it's found. And what does it take? It takes as argument the array A. Let's say it's an integer array, key and integer n, the number of elements in the array. And let's say I have a variable int I which traverses through the array, and I is assigned the value of 1. And while I less than or equal to, again, I'm going to assume that the indices go from 1 to n. And let's say an unsorted array, this is what we're looking at. Let's say these are the elements in the unsorted array. So I start with the index 1, I equal to 1. So while I less than or equal to n and key is not equal to a of I, do I plus plus. Okay. And if I is greater than n, then we know that the element has not been found. And return -1, else return I. So what is the point of this algorithm? So we search through the entire array, starting from 1, we increment it, check whether the variable is this, and as soon as it reaches n, and you not found the element because key is not equal to AFI, you want to exit from the loop. And this condition, I'm assuming it's kind of a dirty compiler, so it will not evaluate both of them because otherwise you could get a array index out. Okay. So what is the worst case time complexity of this algorithm? Complexity is clearly log order n. Okay, because the worst case, I'm looking for the last element or an element which is larger than the last element, and this is the complexity. So can we do better? Do better. So we have to do some pre-processing. Suppose we subject the array to sorting before searching. Then we can do a little bit better. And let's say the same array is sorted. Three, 8, 14, 18, 20, 35, 39, and 41 sorted. Then what do I need to look for? Let's take, so in this particular case, no, let's say I was checking for the key -1 or something like that. It could be anywhere in the array. So to search through the entire array. Suppose I'm looking for the same key -1 in this sorted array. Then what we can do is we realize that the first element itself is larger than -1, and we can straight away exit. That is the advantage of even when I'm performing linear search when I'm looking for an element. So this algorithm, which we call another version of linear search, looks something like this. Again, it takes the array A and int key and int n, the size of the array. Again, I will start with, let me call int I for traversing the array. I assign I equal to 1. While I, again, less than or equal to n. And the difference is now just look at this. We're going to change this. Key less than A of I plus plus. Okay. Same. And then if A of I equals key, then return I, else return -1. Okay. End if n. So what is the difference between what is the input to the program? Of course, we are assuming that A of 1 to n is sorted and n is greater than 0, and what is it that we can assert here? Either key in belongs to array 1 to n, or key does not belong to array 1 to n. Okay, that's all that we can assert over here. And what else do we see here? Notice that what is the time complexity of this algorithm? So the important point is it does not have to go to the end of the array to search for a key. Like we saw of -1, first comparison itself, it will come out. And let's say you're looking for the number 19 as a key. You come here, it comes across 20, and it finds that it's not less than a of I. Okay. So what is it going to do? It will stop. Okay. So key less than a of I. Okay. Do I plus plus. Now a of I minus 1. So it should be if a of I less than or equal to n and key less than or less than a of I. Okay, it's not less than, it could be equal to, and it stops here. So it returns with the element. If the element is equal to the key, then it will give you the correct answer. Okay. So this is still not exploiting in a very big way the structure in the array. Can we do better? And that is what binary search is all about. What do we do in binary search? We have int star a again here, int key and int n. And what we're going to do is we're going to do something different over here. See, since it's already sorted, I can somehow use the fact that there is an order in the array. What do we have? Again here, 3, 8, 14, 18, 20, 35, 39, and 41. Okay. So what we can do is, let's look at the middle element. Let's say this is 1 and this is 8. And so basically, we look at the middle element. What is the middle element here? Mid is 4. We check whether the given key, suppose I'm looking at key equal to 19, is less than or greater than the value in the middle, at the value of 4. It realizes it's greater than. And then we say, move this, let me call this pointer as the lower end of the array, this at the upper end of the array. We move this pointer lower to this position because we know that all the elements here are smaller than 90. Okay? Then we search in this part of the array. Again, look at the middle of this. So this is 5 plus 8, 13 by 2, and this is again, location is 6. We compare with this, we know that 19 is less than 35. So if at all we find it, we should find it in this portion of the array. So now we have what? 5 and 6, and the index should be 5. So middle value is 5 here. And we compare it with 5, and we notice that it is still smaller than 5. Then obviously this portion, so it should be below this, but now the lower and the middle have crossed. For example, lower and upper have crossed, so this becomes upper here. And once they have crossed, you exit. So let us see how to write this algorithm. And we'll try it with different examples. So, okay, on the other hand, so notice that to get to the element 19, to see whether the element 19 was there, I had to check 1, 2, and a third element. At most 4 elements has to be checked. Here too, we have to check up to 5 elements over here. If it was this element, you have to check 7 times and so on. So this will also, in the worst case, be a theta n algorithm in terms of complexity. But we will see that binary search we can do much better. We'll see that in a little while. So let's write the function module here. And binary search of int star a, int key, and int n. Okay. We maintain variables lower, upper, and middle. So initially we set lower to be 1, upper to be n, and middle is lower plus upper divided by 2. So we look at the middle element. Then we do what is called a repeat until process where, sorry, I this statement comes within the repeat. Repeat middle is assigned the value of lower plus upper by 2, and if, as I already explained to you, if the key is greater than A of middle, then lower is assigned the value of middle plus 1. Otherwise, upper is assigned the value of middle minus 1. Okay, end. And we repeat this. So basically, we are changing the nibble in the array where we perform the search, where we know if at all the element is found, it must be found there. Until A of I equals, A of middle is equal to the key, or lower becomes greater than upper. Okay, this is the binary search algorithm, and if lower is greater than upper, we return -1, otherwise we return the middle index. Okay? And if and module. So let's take an example, a few examples, and see how this works. Okay. So we're talking about a sorted array. I'm going to take an even simpler example. Let's say I have 2, 4, 6, 8, 10, 12, 14, and 16. And let's say that the key is 9. So what happens? Initially lower is here, upper is here, and this is middle. Then clearly 9 is greater than the middle value. Therefore, we update lower here, for example, middle plus 1. This is lower now. Let me call it lower prime, and this is upper. Now, what we do is we look at lower primes as upper prime. So this is 5 plus 8, 13 by 2. This is the sixth value. And let's say this is the new middle value that we're looking at, middle prime. And clearly the value is smaller than this. Therefore, we set lower to be 5. So this is 1, 2, 3, 4, 5, 6, 7, 8. So what do we do? 8 plus 6, lower was at 5, and this was 6 over here. And we compared with 6 and we found that it was smaller than 6. Therefore, now what happens? You have upper over here, and upper plus lower prime, upper prime for that matter, is equal to 5. And we notice that the value of key equal to 9 is smaller than the middle value. Therefore, what happens now? The new upper prime points here, upper double prime. That means what? This implies lower becomes greater than upper, and we terminate the algorithm. So this is one example. And let's say we're looking at key equal to 10. I'll write it in the form of a table: lower, upper, and mid. Let's say I have 1, 8, and 4. So 5, 8, 6, 5, 5, 5, and A of middle at the 5th index, for example, you have the 10th element, so you exit. And let's look at key equal to -1. And we see lower, upper, and mid. 1, 8, this gives us 4. Then we know it's less than the element at the location 4, which is 8. 1, 3, and 2. And we know that this will be 1, 1, and 1. And then lower will become smaller than 1. Again, upper becomes smaller than 1. Therefore, again, you have lower greater than upper and the exit. Okay. So what do we see now? If you look at it, how many here, for example, the 3 comparisons. Here we will do 4 comparisons, 4 comparisons. Therefore, in terms of the size of the array, the complexity is order of log n, okay, or theta of log of n. You can use either product rule or sum rule to show, and product rule and sum rules to prove this property, that it's only log n in terms of complexity, the binary search algorithm. Oops. Now let me take, we divided the array in binary search into 2 parts. So nothing prevents us in doing what is called ternary search. If you have a very large array, you can divide it into 10 parts maybe, or 15 parts or whatever, and search. But of course, you'll have to do many such comparisons. And these kind of algorithms also exist for searching. For those of you who are interested in sorting and searching algorithms, there is a book by Knut on searching and sorting. An excellent book. You have time as a computer scientist, you must read this book. We will do the other sorting algorithms, which are a little more complicated, in the next one. We'll stop here for today.